Well, here we are with Unit 6B, Thermodynamics. This is Lesson A, Temperature and Heat Transfer. On our first video, we're looking at temperature and heat flow. So we're going to be looking at how we measure temperature, what it is, and how heat flows from one place to another. We're going to be focused on heat transferring by conduction and also what's called the mechanical equivalent of heat. So here we go. Kind of the key thing to keep in mind about thermodynamics is that it's really all boils down to small particle motion. Now, when things have motion, they have kinetic energy. So we can talk about thermal energy. That's the total kinetic energy of the particles in a system. So when we talk about particles, what we mean are the molecules and the atoms and the ions from which objects are formed. Right? These particles have kinetic energy. They have motion. In a gas, the particles are free to zip all over the place and bounce off of other particles. In a liquid, they also kind of flit around, but they make weak bonds with each other and tend to kind of clump together. And in a solid, the particles are bound together with chemical bonds. And these bonds, they're not rigid, so the particles can move back and forth, kind of like they're connected to each other with springs that allow them to vibrate. So to begin, let's talk about some basic definitions of terms that we'll come into contact with as we talk about thermodynamics. Thermal contact. This is when two systems are placed so that they can exchange thermal energy. They don't necessarily need to be in physical contact with each other, but they need to be able to exchange thermal energy. Heat. Heat is thermal energy that's transferred from one system to another. So heat is a process of energy transfer. It requires that there be a temperature difference between two objects. And as long as we have a temperature difference, we can get thermal energy to flow from a higher temperature to a lower temperature. So temperature then. What is temperature? Temperature is the average kinetic energy of the particles in a system. The individual particles of a system move around. They have kinetic energy, and as they move more, there's more temperature. When they move less, there's less temperature. So temperature is just a measure of the average kinetic energy of the particles in that system. And then we've got thermal equilibrium. Thermal equilibrium, just like any equilibrium, is a static state. Objects in thermal contact reach the same average internal energy state. They no longer exchange thermal energy. That's what we call thermal equilibrium. All right, so we will work with each of these terms as we move on. Let's look now at this temperature a little bit more in depth. All right, so temperature is the average kinetic energy of the particles in a system. And we measure temperature then on three primary scales. We've got the Kelvin scale, the Celsius scale, and the Fahrenheit scale. Now here in the U.S., we typically use the Fahrenheit scale, but the Celsius scale is just as easy to understand as the Fahrenheit scale. See, between 0 degrees, which is water freezing, and 100 degrees, which is water boiling on the Celsius scale, there's 100-degree intervals. Between 32 degrees Fahrenheit and 212 degrees Fahrenheit, there's 180 degrees intervals. So what is 1/3 of the way between this 180-degree difference in degrees? It's 90 degrees. That's what we would call hot. If we went outside on a 90-degree day, we'd say this is a really hot day, right? Well, on the Celsius scale, about 1/3 of the way is 33.3 degrees. 33 degrees Celsius is right about 90 degrees Fahrenheit, okay? So 1/3 of the way up the Celsius scale, we would also call hot day, right? Normal room temperature on the Celsius scale is around 22 degrees. Chilly fall weather is about 10 degrees. And when it's really cold, it's 0 degrees, right? Now the Kelvin scale is different in that the Kelvin scale has a true zero. Its zero value represents the lowest possible temperature, which is known as absolute zero. Absolute zero represents the minimum possible energy state for matter. So when reporting a Kelvin temperature, we say it's 301 Kelvin, right? You don't use the word degree with a Kelvin temperature. The size of the units for each scale are the same. So if we want to convert temperatures from Celsius to Kelvin, we typically won't use the Fahrenheit scale. This is just here for us to have something to compare to, we're going to be using the Kelvin and Celsius scale in our treatment of thermodynamics. So to convert from to Celsius, to convert Celsius to Kelvin, you're just going to take the Celsius temperature and add 273, and to convert Kelvins to Celsius, take the Kelvin temperature and subtract 273. That's because there's a difference of 273 Kelvin between 0 degrees Celsius. Okay, so let's talk about something called thermal expansion. So when we add heat, when energy is added to a system by heat, the particles gain kinetic energy. Since their average kinetic energy increases, the temperature will increase. And since the particles have increased their kinetic energy, they move around faster and they move further. Each particle takes up more room, so the object as a whole expands. And it expands in all directions. And we call this thermal expansion. So when structures get built, engineers and architects have to allow for the expansion of materials with temperature increases as they design things, or else the whole thing would break apart on a cold or hot day. Long structures like bridges have what are called expansion joints within them that will allow for that bridge to expand and contract when changing temperatures. And there's a lot of devices in houses. You use what's called a bimetallic strip, where you've got two different metals on that are kind of sandwiched together. Each metal expands a different amount, right? Because all materials have what we call a coefficient of thermal expansion. So each metal will expand, one will expand more than the other, which would cause the strip to curve when the temperature changes. And we can use this to switch electrical circuits on and off, like controlling an air conditioner or a heater. Another example of thermal expansion would be like cracked sidewalks. Those are often due to thermal expansion. Now, while thermal expansion causes objects to expand in all directions, we need to spend a little bit of time looking at what's called linear thermal expansion, where this is the increase of any one dimension of a solid. So the change in length of a solid is directly proportional to the change in its temperature. So if we have an object, it begins at this temperature, we add some energy to it by heat, we can expand it linearly. So here we have its initial temperature and its change in temperature, its initial length and its change in length. So we have an equation to allow us to look at thermal expansion, linear thermal expansion, which tells us that the change in the length of an object is directly proportional to the change in the temperature. And we relate these with the coefficient of linear expansion. For example, if we have a steel railroad track, it's 10 meters long, and at a temperature of 20 degrees Celsius, we don't know its length when its temperature rises to 50 degrees Celsius. We use the thermal expansion equation, and we see that it expands by 3.6 times 10 to the negative 3 meters. And then we add that to its initial length, we see how much longer that railroad track was. Different materials have different coefficients of linear expansion. This equation is provided to you on your equation sheet. Probably see a question or two about it. All right, so let's talk about heat flow or heat transfer. Heat flow and heat transfer are the same, two different terms for the same thing. So heat can flow from one system to another only when there's a temperature difference between the two systems. Okay, so the direction of heat flow is always going to be from a high temperature system to a low temperature system. Heat can only flow in that direction. There's no logical reason for this. After all, it's reasonable to think that in winter heat could flow from the cold outside to the warm inside, right? When you open, it's wintertime, you open up the door, your mom might say, hey, shut the door, you're letting the cold in, right? You're really not, you're letting the heat out. Right, so there's a temperature transfer, there's an energy transfer from the warm room to the cold outside. So direction of heat flow is from a high temperature system to a low temperature system. It only flows in that direction. There's three ways by which heat can be transferred. There's what's called conduction, where heat transfer by direct contact. There's convection, which is heat transfer by a fluid flow. And radiation, which is heat transfer by electromagnetic waves. Our weather systems are really controlled by convection currents, and all the energy we get from the sun comes to us by radiation, right? But we're going to look more detailed at conduction. So materials that allow heat to flow through them easily are called heat conductors, and materials which do not allow heat to flow through them are called heat insulators. Much like when we talked about electricity, we had conductors, we had insulators. So heat conductors are things like metals. Metals are good conductors because of the nature of the chemical bond that binds those atoms together. These bonds, they're called metallic bonds. The significant thing about those bonds is that some of the electrons of each atom are not bound to any one particular atom. They're kind of like a community of electrons belonging to everyone. We call them free electrons. They're loosely held. They can move around. So these free electrons are able to carry heat from one part of the metal to another, just like that with electricity, able to carry that energy from one part to another. They do this through collisions, right? They carry this heat energy by collisions, where one electron gives some of its energy to another, and it can happen really quickly so that the heat transfers quite easily. So if we have a conductor here and we heat up one side of it over here, that heat is going to travel down that conductor to the other side over there by those free electrons. Insulators don't have those handy little particles that can collide with each other, so there's no free electrons to transfer this. So if an insulator is a solid, then the electrons are going to be tightly held through these covalent or ionic bonds. Gases make really good insulators because there aren't many particles to carry the energy from one place to another, right? So they're more spread apart. So most insulators are actually materials that have little pockets of air or some kind of fancy gas in them. That gas will slow the flow of heat way down, right? So like if you think about thermos bottles, those are really interesting. If you put a hot fluid in it, it'll stay hot. You can put a cold fluid in it, it'll stay cold. How does it do that? How does a bottle know what to do to keep things hot or keep things cold? Well, thermos bottles are really simple. They have an external metal or plastic body, and inside that body is a glass bottle. Really good thermos bottles have a vacuum between the outer case and that glass bottle. The glass bottle is mirrored also, so heat is kept flowing by the vacuum, which prevents conduction and convection. The mirror surfaces prevents heat flow by radiation by reflecting the electromagnetic waves. So thermos bottles do a pretty good job of blocking the flow of heat coming either into or out of the bottle, so it can keep hot things hot and cold things cold. Now, of course, we can quantify heat transfer by conduction. So suppose we have a slab of material right here. One side of the material is got hot, the other side has got cold. Say it's like a fireplace or something. We got a fire in here, and this is the brick slab that makes up that fireplace. It's colder on the outside than on where the fire is, right? Now, because of a temperature difference, heat is going to flow through this slab. We call the quantity of heat transferred Q. Okay, we've got here the temperature of the hot side, temperature of the cold side. We've got the thickness of the material we call L, and we've got the area of the surface we call A. So the rate at which heat's transferred through an object is proportional to the amount of heat that travels through the object divided by the time. So H here is our heat flow rate, Q is the quantity of heat transferred, and T is the time in which it's transferred. The amount of heat that makes it through depends on the thickness of the substance, the area of the object, and the thermal properties of the material. The thermal properties are expressed in what's called the thermal conductivity of the substance. Each material has its own value for thermal conductivity. This thermal conductivity is a measure of the ability of a substance to transfer heat. The symbol for thermal conductivity is this K right here. Materials that have a large value for K are good heat conductors. Materials with a low K values make good insulators. So we can call heat flow rate, here we can use this equation. This is heat flow rate by conduction, which is provided to you on your equation sheet. Now, thermal conductivity can have several different values, but units, right? But typically you're going to see you see it measured in units of joules per meter second degrees Celsius. But there are other units for it as well. So since we have two expressions for heat flow rate, we can set them equal to each other. And doing that and solving for heat, we're going to give us the amount of heat flow that would occur in a given amount of time. So that would be this right here. You need to make sure you know how to reach this point. This tells us that the heat is directly proportional to the temperature difference and the area, and indirectly proportional to the thickness of the slab. So if we double the area, we double the heat flow. If we double the temperature difference, we double the heat flow. If we double the time interval, we double the heat flow. If we double the thickness, the heat flow is half. Okay? Now in your reading packet on page 5, you're going to see two different tables of thermal conductivities for various substances. One of the tables gives the thermal conductivities in units of joules per second meter degree Celsius. The other one gives you thermal conductivities in units of watts per meter Kelvin. However, typically when we see a problem, if you need to know the thermal conductivity, it will be given to you. Lastly, the last thing to kind of go over real quick is what's called mechanical equivalent of heat. So one of the great discoveries in physics in the 1800s was made by James Joule, who discovered that heat and mechanical energy were equivalent. Okay? One of the units used to measure heat is the calorie. A calorie is the amount of heat it takes to raise the temperature of 1 cubic centimeter of water by 1 degree Celsius. Well, Joule found that heat could be related to mechanical energy. What he did was he took this insulated container and filled it with water. The temperature of the water could be monitored with a thermometer. In the water tank was a set of paddles that could rotate. So here is a drawing of a cutaway view of this. A piece of line was attached to the paddles and runs over a pulley system. And a weight was attached to the line and released. The weight would fall down, causing the paddle to rotate in the water and doing work. So this was mechanical work being done on that water. The temperature of the water was found to increase, indicating that heat had entered the system, even though it was all insulated. Joule found that the amount of work done by the weight was equal to the thermal energy that increased the water's temperature. So we found that what this means then is that heat and work are simply two different ways of transferring energy to or from a system. So the relationship between the calorie and the joule is 1 calorie equals 4.186 joules. Now this kind of calorie is different than what we would call food calories, right? Food calories are different than regular heat calories. Food calories begin with a capital C and are actually 1,000 heat calories. So 1 food calorie equals 1 kilocalories. Well, that'll do it for this lesson. From here, we're going to go into what's called calorimetry, and we're going to look at phase changes and that sort of thing. We'll see you in class.